Hi everyone, this is Srikanth, Assistant Professor of EEE Department. In this session, I'm going to discuss about the small signal models for transistors. In this, what is small signal model and why we need to go with that small signal model of the transistor, we are going to discuss in this session. So here, the small signal model is nothing but it is the linearized representations that facilitate the analysis of transistors' behavior around a specific operating point. This small signal model is nothing but it is a linearized representations corresponding to the transistors, and that will give the complete analysis of transistors' behavior around a specific operating point. And these models are particularly useful for studying transistors' response to small variations in input signals, allowing engineers to analyze the linear aspects of circuits for applications such as amplification and signal processing. Here, these modeling are particularly very useful for getting the performance of the transistor with a small change in the input, so that we can operate our circuits, electronic circuits, wherever we are using in the application of amplification and signal processing. The two most common types of small signal models are developed for bipolar junction transistors and field effect transistors. There are two different types of small signal models which are developed for BJTs and field effect transistors. Here, the small signal model for BJT is linearizing the transistor's voltage current characteristics. Generally, for any electrical or electronic element, if we consider, the main characteristic is the voltage and current characteristics, which is with a input as a DC operating point. The small signal model for a BJT is based on linearizing the transistor's IV characteristics around the DC operating point. The small signal hybrid pi model is commonly used for NPN transistor. The model consists of For NPN transistor, the model which will be consists of input side and output side. Here the input side we are going to have a voltage controlled current source GM into V6. GM is the conductance and V6 is the voltage which is controlling. Voltage controlled current source we are going to have representing a small signal base current. Here it is a GM into V6 is a base current, and transconductance GM is the ratio of change in collector current to the change in base to emitter voltage. Transconductance is the ratio of collector current to the change in base to emitter voltage. And the second one is the output side, that is at the collector, the output conductance representing a small signal collector current variation due to collector emitter voltage variations. And whereas collector resistance R0, that represents the output resistance. And the next one is the common, that is common terminal what we have considered. Here the common terminal we have considered, if we let us consider it as emitter, and here for common emitter we are going to have Gm into V6. This is the component of collector current, and transconductance Gm is the same as on the input side. And for field effect transistor we are going to have the same input, output and common. Here the input side is with a gate, output side is the drain, and common is the source. Here voltage controlled current source Gm into VGS, gate to source voltage, because here the source is the common terminal representing the small signal gate current. Here voltage controlled current source, remember this one, Gm into VGS, and Gm is the same transconductance, it is the ratio of drain current to the change in gate to source voltage. And output side, output conductance GDS, representing the small signal drain current variation due to drain source voltage changes, and drain source resistance representing the output resistance. And the common one is the source, common source Gm VGS, representing the small signal component of drain current. The transconductance is the same as on the input side. And these small signal models are used in various analysis such as determining voltage and current gains, input and output impedance, and overall circuit response. These small signals usage will be, which is used for analyzing the circuit and determining the voltage and current gains. That is nothing but voltage and current gains are nothing but we can get the input voltage, output voltage if we have the current gain and voltage gain, and input and output impedance and overall circuit response. The transconductance is the key parameter that characterizes the amplifying capability of the transistor. And here by using the small signal models, engineers can analyze and design amplifiers, filters and other electronic circuits with transistors. Here when we are having a small signal model, we can easily analyze and design different electronic circuits. And it is important to note that these small signal models assume small variations around the DC operating point and are valid as long as the input signals remain within the linear region of transistors' IV characteristics. Here BJTs are also capable of amplifying small amplitude signals, and amplifier applications such as these lead us into the small signal model. And this model does not replace the large signal conditions, rather small signal operation is superimposed on the large signal operation. This model which we did we cannot we are not going to replace the large signal conditions, but whereas the operation can be superimposed on the large signal operation. We use the large signal conditions to bias the transistor, and the biasing conditions imposed by a given circuit influence the BJT's small signal behavior. Once after the BJT has been biased, we can focus on the small signal operation, and small signal analysis is easier when we replace with the BJT and with simpler circuit elements that produce the functionality equivalent to that of the transistor. Just remember that these models are relevant only to small signal operation, and furthermore you can't use the models until you have established the large signal bias conditions. The next one is the hybrid pi model. After the BJT biased, we can focus on the small signal models. That is, this is the hybrid pi model. Here we are going to have a resistance R pi and a a controlled current source beta into IB, and this is the collector current, this is the base current, this is the emitter current. This is the pi model of the small signal amplifier. As you can see, it has three terminals corresponding to the BJT's base, collector and emitter. The current flowing into the base is determined by the base to emitter voltage and R pi. What is the current flowing into the base will be determined based on the base to emitter voltage and R pi resistance. And the collector current is generated by a current controlled current source. Just as with a large signal NPN, the collector current flows into the collector, the base current will flow into the base, and the emitter current flows out of the emitter and is the sum of base current and collector current. Emitter current is nothing but the sum of base current and collector current. The collector current, which is equals to beta times the IB, which is not surprising, where IB is determined by VBE and R pi. And this is where the biasing conditions come into play, where R pi is equals to beta by GM, and GM is equals to transconductance, which is equals to IC bias by VT. So we need IB to determine IC. We need the base current in order to determine the collector current, and we need R pi to determine IB, and we need GM to determine R pi, and we need ICB IAS, that is large signal current gain, in order to determine the GM. And it is possible to reformulate the hybrid pi model so that you can calculate directly from VBE to IC. If you replace beta with GM into R pi, if you replace beta with GM into R pi, you have IC is equals to IB into GM into R pi. IB into R pi is equals to VBA, GM into VBA. So we can directly get the collector current. And in some cases, you might prefer to use the following alternative to the hybrid pi model, that is T model. GM into VBE, this is the controlled current source, and this is the RE resistance, emitter resistance. and this is called T model. It looks quite different from the hybrid pi model, but they are both valid in all cases and will produce equal results. With the T model, you need to know the large signal current, collector current, to calculate GM, because the resistance RE is calculated as follows: RE is equals to alpha by GM. You can use the following formula to calculate the parameter alpha, where alpha is equals to beta by beta plus 1. As with the hybrid pi model, the T model can use a voltage or a current as the variable that controls the current source. In the T model, the current source expression is either Gm into VBE or alpha into IE. That is, Gm into VBE can be replaced with alpha into IE. Using the models, what we can get is the BJT small signals models are drop-in replacements for the BJT symbol in a circuit diagram. This BJT small signal models are the drop-in replacements in the BJT symbol on a circuit diagram. Once you have determined the bias conditions, you remove the BJT and insert the small signal model. That is, once we have biased the BJT, then we can replace with a small signal model and connect the previous base, collector and emitter nodes to the model's base, collector and emitter terminals. The next step is not so obvious. You need to replace each DC voltage source with a short circuit and DC current source with a open circuit, as like how we have done in our network theorems. The DC voltage source can be replaced with a short circuit and DC current source will be replaced with a open circuit, because this corresponds to their behavior in the context of small signal operation. Note that a voltage rail that appears in the schematic as simply a supply voltage becomes a ground connection, because the rail is actually shorthand way of drawing a normal voltage source that has one terminal connected to the ground. At this point, you have converted the circuit from large signal to small signal and you are ready to proceed with standard circuit analysis procedures. Now we will go with how we are going to compensate the early effect. First, let us go with the what is early effect. Introduction to the early effect is with a thorough explanation. To make a long story short, early effect refers to a phenomenon that occurs inside the BJT. Early effect is nothing but it is the phenomenon that occurs inside the BJT and causes active mode collector current active mode collector current to be affected by the collector voltage. Active mode collector current is going to be affected by the collector voltage. More specifically, an increase in the collector to emitter voltage will result an increase in the collector current. So when we increase the VCE, directly the collector current increases abruptly. So in order to limit this current, collector current, we have to take some considerations. Here, the early effect, a small signal variable that affects the collector current, that is the base current and emitter current, or base to emitter voltage. If we want small signal models to be more accurate, we need to account for the early effect. Whenever we want the small signal models to be more accurate, that means we need to account for the early effect. Fortunately, this is easily done. All we need a resistor connected between the collector and emitter. How we can reduce the current? By adding a resistance in the circuit. We can reduce the current which is flowing. Here, across the current source, we are placing a ROSS, that is the resistance which is connected, and this resistance will have a path for the current flow that will reduce the complete collector current. And here also this is another type. Here it is connected complete parallel to the both current source and the emitter resistance. And this resistor represents the small signal output resistance, which is calculated as follows. ROSS is equals to VA plus VCE by IC. Here the early voltage VA will often significantly larger than the collector to emitter voltage. So you can simplify this as follows. ROSS is equals to VA by IC bias. In addition, this resistor will make intuitive sense. The early effect tells us that a higher collector to emitter voltage which will result a higher collector current. When there is a resistor, this resistor will provide a path for additional current, and so that the emitter that is directly influenced, that will not directly influenced by the collector to emitter voltage. These are all about the small signal models, and how we are going to design these small signal models is by using the H parameters. What is H parameters? H parameters are known as hybrid parameters. These are set of four linear circuit parameters, that is input ports and output port. Input port will be having input voltage and input current, and output port will be having output voltage and output current. Here, these parameters that describe the relation between voltage and current at the point at the input and output ports of the two port network. And the H parameters are widely used in the analysis and design of electronic circuits. Here, these H parameters are widely used in the analysis of the all electronic circuits, especially for amplifiers and transistor based circuits. Here are some of the applications of H parameters. The first one is the amplifier design. Here the H parameters are commonly used to design and analyze amplifiers both for bipolar junction transistors and field effect transistors. And engineers can use the H parameters in order to determine the voltage gain, current gain, input impedance and output impedance of the amplifier, helping in optimizing the circuit for specific applications. The next one is transistor analysis. The transistor based circuits H parameters provide a compact and convenient way to represent the transistor behavior in terms of a small signal linear model. Here, for transistor based circuits, H parameters provide a compact and convenient way to represent the transistor behavior in terms of a small signal linear model. The H parameters for a transistor can be determined experimentally or extracted from the manufacturer's data sheets and used for analyzing various transistor configurations. The next one is small signal analysis. In small signal analysis, which focuses on the linear behavior of the circuit around its operating point, and H parameters are particularly useful and they help simplify the analysis of linear circuits by providing a linear model that relates small changes in input and output voltages and currents. And the next one is cascading networks. When cascading multiple two-port networks or amplifiers, the H parameters can be used to determine the overall behavior of the cascaded system. When we use the cascading system, the H parameters are used to determine the complete behavior of the cascaded system. And this simplifies the analysis of complex circuits by allowing engineers to analyze individual stages and then combine them. And the control systems, H parameters can be employed to model the feedback network and understand the impact of feedback on the system's stability and performance. Here they help in analyzing the feedback loops and designing systems with desired characteristics. And the radio frequency systems. In radio frequency applications, H parameters are valuable for designing and analyzing the high frequency circuits such as RF amplifiers and mixers. And engineers can use H parameters to optimize the impedance matching and performance of RF systems. And the next one is parameter extraction. Here the H parameters can be extracted from experimental procedures or obtained from manufacturer data sheets. These H parameters data will be provided by the manufacturers that either we can take from that or with the experimental measurements we can get the parameters. And these parameters will provide a valuable tool for predicting the behavior of circuit under different operating conditions. The network analysis, the H parameters facilitate the analysis of network parameters such as input impedance, output impedance, where voltage or current gains are. For voltage gain, it is we are going to get the voltage, and current gain we are going to get the currents corresponding to both input and output terminals. In summary, H parameters find extensive applications in the analysis and design of linear electronic circuits, especially in the amplifier design and thyristor based systems, and they provide a convenient way to represent and analyze the behavior of two-port networks in various applications. Okay, in this session we have discussed the small signal model and what is early effect and how to overcome the early effect, and then what are the applications of H parameters which are used in the small signal analysis of the transistor. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.